When we looked at the spin Hilbert space, we weren't talking about real space. Well, I'm going to start talking about real space because an orbital describes where the heck the electron is. And that where the heck has to be in real space. But we can't just say, oh, it's at point XYZ. That doesn't fly. Instead of that, the electron orbital is involved with probabilities. And here's how the probability thing works. The probability of finding the electron is this weird wave function, which is a complex amplitude. And that wave function, if we take the magnitude of that complex amplitude, and if you remember how to do that from the spin thing, we take the magnitude squared, that's going to give us this probability, or probability density. Okay, it sounds good. So how many of these dimensions do we need to describe all these points in real space? Well, how many points are in real space? Infinite. So, if we have an infinite dimensioned Hilbert space to accommodate all these complex amplitudes, then a single vector in that dimensional space will suffice as long as we have an infinite dimensioned Hilbert space, because we have an infinite number of points. Now, to predict finite probabilities, so that the probabilities aren't infinity or something like that, the space consists of, and this is the mind bender, this is the alphabet soup here, all square integrable functions. Square integrable functions? How the heck do I know what a square integrable function is? Let me start with something that makes perfectly honest sense, which doesn't happen that often in this subject. The probability of finding the electron somewhere in real space has got to be 1. In other words, if it exists at all, the probability of finding it somewhere has got to be 1. And when we calculate probability, we take the square of this function, and this function will give us this 1 value if this function is, first of all, integrable in the Hilbert space. So the function has to be designed such that it's integrable. In other words, it's not infinity. I hope that clears things up a bit. This function up here must be complex. One of the reasons is to solve the probability, but maybe an easier way to say it is it must be complex in order to solve the Schrödinger equation. If you watch that series on developing it based on the Schrödinger equation, then I think you can appreciate that a little bit more, because wave functions involve e to the I phi. Ooh, I. So e to the I phi, there's that complex part, so it has to be complex. Now this can be anywhere in physical space. So this r value must have infinite dimensions. That might be a little hard to wrap your head around, but if it can be anywhere, then each one of these things has a complex space, so we've got to have infinite number of those things. Not to say that we look at all the infinite dimensions, but we have an operator, the Hamiltonian, which will help us out fix all that stuff. And so our Hilbert space here has infinite complex outcomes depending on where we are in real space. Now, before we go on with more of my gibberish on the board, let's look at some solutions to the Schrödinger equation, but we'll look at them as representations in shapes within that space. Wouldn't that be fun? Some pictures. We need some pictures, and we need very pretty pictures. Remember earlier how I said that I don't like pictures? Well, I'm going to bend that rule a little bit because I want to show that an electron is not a point, and I want to show that the electron is a probability distribution. Here's our old friend hydrogen. And the hydrogen electron is not a ball spinning around the radius. This is all of the electron. The probability of the electron is represented by this shape outside the nucleus. Okay? Well, how do you think this shape would change if I added one more electron to helium? Can helium's 2 electrons share the same orbital space? Tick-tock, tick-tock. What's the answer? Well, helium, of course they can. In some energy configurations, they can. So this shape didn't change, and this 1s, it's kind of like a spherical shape, is the same as hydrogen. So you think, what's the difference between helium and hydrogen? Well, you know the answer. There's an extra electron down here. Now, there are some allowed states where if both of these electrons have the same spin, one kicks up into the 2s. We'll have to deal with the Hamiltonian to answer some of those questions. Now, let's say, okay, lithium. What happens with lithium? Well, with lithium, we've got a 3rd electron, and the first 2 occupy here. Now let's see what happens to the picture. Let's see if the picture changes any. Well, they show a blue around the red core here. So what's that blue indicate? Well, that indicates that there's a high probability of finding the electron out in this area. It's farther away from the nucleus. That's the safest way to say it. And what do you think would happen to beryllium? Would beryllium change this photo? It's not a photo, it's a picture. It's somebody's brain thinking. Let's see what happens here with beryllium. No change. We've learned that with lithium even with lithium, that we can end up occupying some of these p orbitals. But we'll have to investigate this. This looks interesting because there's 3 p orbitals. Now we'll get into later why it's s, p, d, f. Those all come from names they had for the spectral imaging, that they spectroscopy. But it doesn't really apply to what way our brains should be thinking. Let's just say this is a little history lesson with the SPDF. So let's see what happens after we fill the 2s orbital with that other spin electron. And let's go on to boron. Ooh, it's green. Ooh, you know what? I think we're going to get a p orbital. So let's see if the p is just another shape around this blue, and so we get a... Let's just see what happens. Let's just plug it in and see what happens. What in the Sam Hill is that all about? What is this? I've got 2 of these things. Now, what would happen if I go to the next 2 elements and start filling up those p orbitals? Well, let's see. Now, watch carefully what changes when I go to carbon. Oh, the orientation changed. What? Why would the orientation change? Well, I bumped up to another one. So apparently the energy thing only allows us to, the next energy level or next electron just doesn't fill in this other p. So that's a strange relationship. And let's go on to nitrogen. I'm going to guess that it puts another different orientation than boron or carbon. Da, 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 da. We filled those in. Now, how many elements are left in this row. We've got oxygen, fluorine, and neon. I'm going to guess that we have to fill in these spins now. Fill all of these. So we've actually got what? We added 3 electrons and the shape didn't really change other than the orientation. Now it seems like those would be exactly the same atoms, but it doesn't work that way. They've got different numbers of electrons. So here's oxygen. Okay, that kind of looked like boron, didn't it? Let's go back to boron. Yeah, it looks just like boron. But we're filling in another electron there for oxygen. And fluorine, I bet fluorine looks like carbon. Place your bets, place your bets. Yep. And then neon, to round this all out, we got one of our second noble gases in the periodic table. There's neon. So look at that. We had to fill in all of these before we went to this. So these p orbitals they're very interesting to me. How could it be that we change all of these shapes just to get to that? And one more. I'm not going to do this all day, but one more. Let's look at sodium and see what that looks like. Well, one thing before I plug this thing in, sodium's going to have 1 lone electron. So let's see what happens to sodium. There's the little hydrogen and helium orbital. Here's the lithium orbital, but we can't see the shapes for those p orbitals. They're kind of hidden in there. And so this it forms a shell around all of it. Okay, enough of that. The pictures, remember, are representations of mathematical probabilities. They are not in space. We do not have a shell in space. These are just the probabilities of where those electrons are. And one thing to note is, as we add electrons, notice the effective radius of the atom becomes greater, which that seems to fit. That seems to fit. Higher energy, we get the probabilities farther away from the nucleus. Wasn't that fun? I enjoy this so much. I was looking forward to doing it.